इसको ऊपर में रखना चाहता हूँ. Okay, Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Now, you see, last time now, first of all, let me apologize for late class. Actually, I was just stuck in something extremely important. A few people came to meet me, and I wanted to make sure that I talk to them. ये लीजिए, इसको ले लीजिए. Okay, and I hope we'll be able to make it up. Number two, you see, the way we are actually proceeding, unfortunately, my own expectation is that in order to complete NMR spectroscopy, at least with reference to solid state NMR spectroscopy, its contribution in drug development, medical diagnosis, and other fields of sciences, and as well as some most important techniques in NMR spectroscopy, I would probably need another 3-4 lectures in addition to today. So I don't know whether you're willing to do that. If you're willing to do that, I'll be very happy to come and discuss these techniques with you, because the original plan of having about 13-14 lectures has not been successful because of I think the different level of understanding which exists among the audience, not only here but also in other universities. So if you are willing, then we can proceed and have one more session of one more week of teaching next week, which primarily means about 4 or 5 additional classes, or 3 or 4 additional classes of NMR spectroscopy. What do you think about it? Huh? Sure, that is important. What about other universities? Do you have any clash with some other course which you want to attend, or you would be able to spare one more week for NMR?
Sure, sir.
I
It
need
will
to.
be okay for us.
It is okay for you and other universities, University of Karachi, LAMS, Balochistan. Anybody has any objection or a problem?
Sir, we also have a second term that from April.
And for classes of coursework, your coursework starts from when?
From 1st April, sir.
Okay. So, you think I will not be able to attend it?
Of course, sir, we will not be able to attend.
Okay. Let's work this week, and next week whoever is available can proceed and can participate, but I will try my best to at least give you the glimpses of the most important techniques in NMR spectroscopy this week. Now, this is what I have been discussing with you last time. I start discussing with you the basic fundamental concept of two-dimensional NMR spectroscopy. And I told you that the primary difference between one-dimensional NMR and two-dimensional NMR is the introduction of an evolution time. Evolution time is small t1. And we also understood that during this evolution time, which is increased uniformly incremented in every experiment, which is called transient, there are certain changes which takes place in the magnetization which is present on XY plane. We understood that this modulation, these changes, because of evolution time, is eventually translated into frequency domain, and this is the spectrum which we actually discussed, that these are stacked plots. These are the one peak NMR spectrum of a compound in which we have only one proton or one group of proton, and that every spectrum is actually representing a different transient or of a different experiment, and these experiments are different from each other only because of T1 time, evolution time. And we understood that this evolution time, since it is different, the FIDs would be different, and as a result the frequency, amplitude of frequency is different. So this is just a stacked plot in which we have number of spectra put together in a transposition manner, and each peak, each spectrum has a same peak but different in amplitude, and this amplitude is different because of T1 time. So what is actually happening during the T1 time is actually affecting the amplitude of the peak of the signal, and eventually if you see them, put them together in a transposition manner, you generate a pseudo FID, which is also called interferogram, which is different from each other only because of T1 time. And this T1 time is then go through a second Fourier transformation. As a result, the second Fourier transformation will give you a second frequency, and this is the key of the two-dimensional NMR spectroscopy. Always remember that this is what happened during the T1 time will give you an additional dimension. Always remember, I want to make it clear to everyone that this is during the evolution time, because preparation, mixing, everything is same in transients. The only thing which is different from in one two-dimensional experiment to the other experiment is primarily the T1 time, evolution time. And because of this uniformly increased T1 time, you see a difference in amplitude of the peak. Otherwise, until they all fade away because of the relaxation and go out of the XY plane, you see a gradual decline in the amplitude until it becomes nil. And as I said that this pseudo FIDs, this pseudo FID which you generate by putting frequency domain spectrum together, and you have a frequency at one end and the T1 the other end, because T1 makes them different, you get a pseudo FID, and this pseudo FID will eventually convert into a second dimension. Now, always remember that this change in amplitude during the T1 is the on which you generate so-called second dimension. Imagine that if you have a same amplitude throughout, you would not be able to get a second dimension. So the second dimension is coming because of the difference in amplitude due to an evolutionary process during T1. Okay, and you can add as many dimension as you wish. So you can have T1 and you can have another evolution time, and then you convert your spectrum into three-dimensional spectrum. So dimensionality in NMR spectroscopy is primarily introducing incremented time delay. In NMR spectroscopy, dimensionality primarily means introducing an incremented time delay from one transient to the other transient. And this is the beautiful two-dimensional NMR pulse sequence. And as I said that you do a second frequency transformation, you get a plot like this. Now, you get a plot like this, which is actually 4 peaks. These are the diagonal peaks, and these are the off-diagonal peaks. And this plot is you have F2 and F1. So you primarily have 2 different frequencies. This plot is a beautiful plot, but it's a useless plot because you cannot use it for a complex spectrum. Therefore, you do not really use this stack plot, and instead of that, you actually use a contour plot in which you see these peaks from top to bottom, like this. So you see these peaks from top to bottom. These are diagonal peaks, and these are off-diagonal peak. Off OFF, off diagonal, away from the diagonal peaks. These peaks are unmodulated, and these peaks are modulated peaks. Remember this correlated spectroscopy, which is the workhorse of NMR spectroscopy, is the one two-dimensional technique which is used the maximum. Homonuclear correlated spectroscopy, proton-proton is the most important correlated spectroscopy, and we have learned that COSY is a beautiful technique. Then we also learned that there are various stages almost similar to one-dimensional NMR, but the only difference is that you do a 2 different Fourier transformation, one Fourier transformation and the second Fourier transformation, and as a result you get a 2-dimensional spectrum. And then I told you that there are various different techniques which people use for a variety of different types of purposes. Scalar coupling, the direct coupling is determined by a COSY spectrum. Homonuclear TOCSY is a total correlation, multiple quantum. Dipolar or a vector couplings through space coupling is measured by a technique called nuclear Overhauser effect spectroscopy or NOESY. And then you have heteronuclear coupling also, proton-carbon, heteronuclear TOCSY, which is proton-carbon also. This is proton-carbon. You can have proton-carbon in long range. You can have NOESY HSQC and NOESY HMQC techniques also. This is the graph. This is primarily the diagram on which we spend considerable time in order to understand correlated spectroscopy, and I told you that correlated spectroscopy is unfortunately very poorly described in most of the book, and I tried my best to actually give you glimpses of the understanding of, for instance, this molecule, which is pentose sugar, is a molecule in which you would be able to see lots of different interaction. So if you have, this is correlated spectroscopy, you make a line from this corner to this corner, and this is your diagonal peak. This is your diagonal peak, and the rest are of diagonal peaks. And I told you that the technique is extremely simple. You just draw a horizontal line and a vertical line, and then it will tell you that this proton is connected to this proton, and this proton is connected to this proton also, and this proton is connected to I don't know where. But you see the 4-5 proton, which if you look into the structure, 4 and 5 proton, this proton, methine, and this methine proton are almost overlapping, right? So you see no interaction between them because they are just so close to each other, and here your COSY fails. This is the technique, a failure of a technique where closely placed peaks which are overlapping to each other cannot be distinguished. Now, if I tell you that, tell me which proton is connected to C6 and C7, you would have a great deal of difficulty in telling me that it is 4 or 5. It's not so easy. It's not trivial. And remember, it's a small molecule. If you have a very complex molecule, the overlapping can be extremely serious, and that overlapping is the failure of COSY, correlated spectroscopy. The second problem with the correlated spectroscopy is that you cannot distinguish between geminal and vicinal couplings. They both appear as a cross peaks or so-called off-diagonal peak. For example, in this case, the coupling between 2 and 3, which is a vicinal coupling, and a coupling between C6 proton, CH2 protons, geminal coupling cannot be distinguished. So you cannot distinguish between geminal coupling and vicinal coupling in correlated spectroscopy. You also have a problem that you cannot distinguish between W coupling. Sometimes you have a W coupling. This proton is coupled with this proton, and you get a W coupling also. So sometimes it is rather difficult to distinguish between W couplings, which are also scalar couplings, but they are visible in correlated spectroscopy. This is an interesting structure of this molecule. See, when I say homonuclear NMR spectroscopy, that doesn't really mean that it is only between proton and proton. This molecule, which is just phosphorus, all of them, I don't know what is, it looked like a fountain or something like this. When you look into the structure of it, you would have absolutely the similar type of contours. You would have a similar type of cross peaks as you see in proton-proton. So always remember that though we are organic chemists and we very often talk about proton-proton coupling, but it is equally valid for phosphorus-phosphorus coupling, or for nitrogen-nitrogen coupling, or fluorine-fluorine coupling. So for example, in this case, you see the coupling between 1 and 5 and coupling with other between different phosphorus. So it is an equally valid technique. Now, what I was trying to convince to you, correlated spectroscopy, was that it is rather difficult to explain by a vector diagram. But I tried my best to explain correlated spectroscopy by using ENEP sequence, in which I told you that the first 90 pulse will bring your magnetization vector to Y, and then this would split because of, if it is an AX system, the A will split because of X into doublet, and X will split into doublet because of A. And as you will bring it within 90 pulse, you would see during the T1, and remember T1 is an incremented time delay. This is the best diagram I got so far. I really work extremely hard to get this diagram. And I think it will tell you the COSY forever. COSY, you would become the master of COSY, During the T1, during the T1 evolution time, this would split. Imagine it is only A, it's much easier to handle one proton than handling two protons together. So this is A, which is split into two, a slower moving and a faster moving. So split into two. When it is in phase, you provide a 90 pulse. When it is in phase, you would provide a 90 pulse and you would not see any difference in them. But if they are anti-phase, if they go away from each other, you give enough time that this doublet is split into a place where it is on -x and -y. Then if you give a y pulse, then what will happen? It will go to z and -z. And this is a condition which is called polarization transfer. So remember, depending on the T1, you can either handling when T1 is close to, when T1 is small, you're handling something close to in-phase component when they are not splitted so much. But when T1 is larger, you would be handling something which is close to antiphase. And these signals which are close to in phase are the non-modulated diagonal peaks, right? And the signals which are close to antiphase are the ones which are actually transferred to the partner by using the same concept of polarization transfer. And these are the modulated peak, because now A is modulated because of X, because it mixes population with the X, and X is modulated because of A, and therefore its chemical shift would move to X and A would move to Y, and then you would see an off-diagonal peak. Now, if somebody has any problem with it, let me know, because this is the best diagram I could get for correlated spectroscopy. This is the best. Any problem with it? Very, very simple, that when you have T1 evolution time less, then these two components are not divided so much. And they are not divided so much, so Y pulse would not really bring them to Z and negative Z. But when they are moved apart from each other, after a considerable time delay, closer to this position, remember ये जो दो है ना, ये आपको सिर्फ position बताई जा रही है, that it can be like this and it can split into two components. When it is close to this, these are non-modulated, and when it is close to this, they are the one which would transfer the population. And since they would transfer the population, this is going to be a correlation, so-called polarization transfer from one proton to the other proton. Exactly the same philosophy as you have in proton-carbon, but is different because it is the case of homonuclear proton transfer. Remember, anything which is close to anti-phase component will give you cross peaks. And anything which is close to in phase will give you non-modulated diagonal peaks. Okay? Khalas? Anything else? Yahi? Okay? I'm willing to spend the rest of my life in explaining this diagram if you have any problem. Okay, I want some volunteer to explain it to me. Because it's not because I want to judge the level of knowledge of someone. I just want to know whether this can be explained in some other language or some other words. Sorry. Volunteer. Who would volunteer? Molecular medicine? No? Hina? No? Okay. Anybody please? It means that it is absolutely unclear to you. Because out of so many people, not a single one is willing to explain it to me. In different languages, okay.
Explained by us.
Be explained by us. Okay, now, ये समझ में आ गया? हाँ? ये किसकी वजह से हुआ है? हाँ? 90x plus. And what is this? And this T1 can be 0. And when T1 is 0, the 90 Y plus will bring it. Now, okay. So, and if T1 is 1, 2, 3, 4, 5, 6, 7 and 8, what will happen? क्या change होगी? That they split and go away from each other, right? So they move from this condition to this condition, right? यहाँ भी गड़बड़ हो जाती है. क्यों भाई? ये तो split हो रहा है ना? It's just splitting. वो तो अभी हम बाद में लाएंगे, इतनी जल्दी नहीं करेंगे. ठीक है? अभी थोड़ा प्याज को पकने दें. क्या कहते हैं वो? गुलाबी होने दें. अच्छा, so you're convinced that they are moving away from each other, right? And they are moving away from each other based on the duration of T1, right? And eventually they would reach to this particular antiphase situation. ठीक है? At this position, if you give a Y, you would have Z and negative Z. So anything which is close to antiphase will be able to modulate a partner nucleus. Anything which is away from the antiphase and close to in phase, this is called in phase. They have not really changed their phase. When they are close to each other, where they have not really split it from each other, would give you a non-modulated diagonal peaks. Anything which has reached to a stage closer to it, antiphase, not necessarily 100% like this, can be close to it, then the Vipers will bring them closer to Z and minus Z. And this situation would be a situation in which you would see a polarization transfer from A to X and X to. As a result, they are modulated. They are modulated for each other, and therefore these peaks, which would be the result of a Y pulse to antiphase signal, will give you cross peaks of diagonal peaks. And anything which is close to in phase component will give you non-modulated peaks. Okay? Please. Thank you. Okay. God, they're not properly placed. Okay, we've gone through interpretation of some spectra, and I wanted to discuss with you inadequate also, and I said that I would discuss this with you in terms of a two-dimensional NMR technique, because it is much easier to interpret inadequate with reference to two-dimensional NMR spectroscopy. Remember, this is C13 homonuclear shift correlation. These are very dilute and rare cases where you would have two C13s together, 1 in 10,000, And these C13 couplings compete with a strong carbon-13 signal, which is 1% of the total carbon value, and it is 1 in 10,000. Therefore, there is always a problem of suppressing a big peak of C13 nucleus. And I showed you a particular pulse sequence through which you can separate the C13 large big peak of C13 from a satellite peak, which is because of the homonuclear coupling between two C13 C13 spectrum. And this is really very, very easy. Starting from this molecule is a very simple molecule, only 4 carbon, and this is the most downfield carbon. So you have this signal is coupled to this particular carbon, which is at 35. So this is C2. So you make a horizontal line and then you make a vertical line, and this vertical line you connect it with the other. So this C2 is connected to C3 and this C3 is connected to C4. Interpretation is extremely easy, very, very easy. You just need to make a one horizontal line and a vertical line straight. I will tell you that 1 is connected to 2 and 2 is connected to 3 and 3 is connected to 4, and that's how you get the carbon framework. I told you that everything else will give you indirect coupling, but inadequate is an experiment which gives you coupling between the carbon and carbon framework, and it is a very desirable, extremely powerful and robust technique which is used to determine the structure, but it has an insensitivity problem. This is relatively more difficult type of molecule in which we have lots of carbon, but the philosophy is exactly identical. You start with the most downfield proton, let's say this one, you make a straight line, so 12C12 is connected to something which is at 78 or something like this. Then you make a straight line to this place. If you make a straight line, a vertical line, then you draw on your right side another line, means C11 is connected to C13. So that's how you get this. Is 19, the 19 is connected to 22. That's how you get the full framework of carbon. Very, very easy. You need to have a straight horizontal line and then a vertical line to make them together. For instance, this 18 is connected to 19. You make a straight line, you'll get 19 here, and 19 is connected to 22, right? So that's how you get the full framework of all the carbons within a molecule, and this technique is extremely powerful as a two-dimension technique because you spread the magnetization into 2 different dimensions, 2 different frequencies. Now, I want to tell you, I want to move forward to a very important technique which is called total correlation spectroscopy. Now, total correlation spectroscopy is also called homonuclear Hartmann-Hahn spectroscopy, or HOHA, homonuclear Hartmann-Hahn spectroscopy, and it's almost synonymous, although the pulse sequence is substantially different, but the end result is quite same, and this gives you an excellent correlation between these. Now, doing the TOCSY is an interesting technique because it has an evolution time T1, and magnetization is spin locked by series, but this mixing time, the magnetization exchange through scalar coupling. Without going into detail of it, I want to just show you what this primarily means. This is the technique in which you have a pulse sequence. There are only 2 pulses. This is 90x pulse, which bring your magnetization vector to the xy plane, and it is different from the COSY because in COSY you have another 90 pulse. In this case, you have a series of pulses together. They're called train of pulses or Malif 16 pulses, about 16 different pulses together. And they are so-called trim pulses with a small delay in between. There are several pulses together. And you see that these are just several pulses. So you have a delay, you have a 180 Y pulse, and then you have a delay. You have a 180 Y pulse, a delay, 180 Y pulse, and delay, and 180 Y pulse, and they are all together. There are about 16 of these pulses. There can be more than that. Now, question is, if I bring my magnetization vector by 90x to Y, and if I start giving these pulses, what will happen? Remain at the same position. So what is actually happening, this 180 Y pulses are kind of a spin echo pulses because they would split because of chemical shift and coupling constant. When they will split because of the chemical shift, the 180 Y pulse will bring them together again. This is called spin echo pulse. Spin echo pulse. So they would be together, the same place, at the same time, and they're called spin locked. All of them have been spin locked. All of them were put together in the spin locked position. Question is that the component of splitting because of coupling, can we make them together at the same time? No, never. Remember, in a homonuclear system, you can only mix the chemical shifts together, but not the coupling constant. The coupling remain divergence, because of a simple reason, as I told you, that if A is split because of X, and they're moving like this, and if you give a 180x pulse, the X is also changed. And when X is also changed, the coupling, the splitting because of the coupling would never be together. It's only the chemical shift you can put them together, but not the coupling. Agree with me? Fully convinced? And this is the beautiful Toxie spectrum. What is actually happening is you are giving an incremented T1 so-called evolution time during which this split, and then you give a 180, you give a 180 Y pulse. When you give a 180 Y pulse, because shifts, they all come together in a different position. Remember, in T2 detection time, they would not be as coherent as you see from here. They can never be, because with the increased T1, they would be different at a different position. Okay? So with a T1 is making them different. Although they are spin locked, but the effect of chemical shift is still present. Now mujhe bataye if you can explain this thing, because it's a very, very fine point, extremely fine point. Very fine point. Remember, this particular time duration is fixed. It's called mixing time. It is fixed for all experiments. In one, I give a T1 like a 1 second. So you have a splitting of a signal because of chemical shift like this, right? When I give a 180 Y pulse, they move like this and they will start coming close to each other. But when there is a big T1, मैं अपनी उंगलियां तोड़ नहीं सकता वरना ये caught like this, So if they are a big T1, then they would be far away from each other, right? Far away from each other, and then 180 Y pulse will change the mirror image position, but they would never be collapse together at the same time, because this is same for the whole experiment. So in initial T1 time, where the splitting is not that much, you would see a complete coherence. But in a larger T1 time, you would see them at a different position. So the effect of chemical shift, despite the fact that they have been locked together, are different based on the T1 time. So the chemical shift remain valid. The most important part of the whole story is that the coupling constant, the splitting because of the coupling constant would never be converged together. Would never converge. Only the chemical shift will be locked with each other due to a sequence of 180Y pulses which called spin-echo pulses. But because of the coupling constant, the splitting because of the coupling constant will remain diverge, and as a result you get a spectrum in which all proton of a spin system, all proton of the spin system would have a similar chemical shift, but they have a different coupling constant because coupling constant has not been merged together. So for example, in this molecule, you see this is the same molecule which we see a COSY 45 spectrum just now. But in this case, you see the coupling between 6 and 5, and coupling between 6 and 6, and coupling between 5 and 4, and 4 and 3, and 3 and 2 are the geminal and vicinal couplings which were visible in COSY spectrum as a discrete peak. But in this particular case, you see everything within the spin system, everything in the spin system is coupled to each other, which primarily means that 6 will be coupled with 1, 6 will be coupled with 3, 2 will be coupled with 6, 4 will be coupled with 1, everything in the spin system. What is a spin system? A spin system is a system in which you have unbroken coupling chain. Unbroken coupling chain. And how you break the coupling? In the presence of an oxygen or presence of a quaternary carbon or presence of a carbonyl group or presence of nitrogen or whatever. Not nitrogen, but tertiary nitrogen with substituent. So you see in this case there is one coupling, this is one chemical shift, this is one spin system, and this is the second spin system. The second spin system is not shown here. What you see the spin system between C2, C3, C4, C5, C6, and all of them are seen together. Now, I want to translate it into a very easy language. What you have done is the following. You bring them together at the same time on XY plane, and then you lock all of these spins together at the same time by using a train of 180 pulses. So they all are strongly coupled with each other. In the COSY, you don't see this coupling. In the COSY, you see only geminal coupling and vicinal coupling. But in this particular case, you brought them together by using a train of pulses, so-called spin lock. When you spin lock the whole thing, they would be all coupled with each other because they are strongly interacting with each other. They have been just mixed together so strongly that they would all behave like a same as exist and like same chemical shift. But on the other hand, the coupling would remain operational. Splitting because of coupling would remain operational, and as a result, you see that C6, C6 prime, 4, 5, 3 and 2, they all are coupled to each other. They all are coupled to each other. It's a very powerful technique, total correlation spectroscopy, and this technique is now extensively used. Now, it's not only the two-dimensional experiment, but you can in fact have you can record them as a one-dimensional TOCSY2. For instance, this is the NMR spectrum of the whole molecule. And now I invite you to think very carefully, this molecule is comprised of at least 3 different spin systems apart from this cyclopropane, apart from this cyclopropyl group. So you see this, in this case, you have a very complex proton NMR spectrum. This is D, a spin system which extends from this, and this spin system, and of course this spin system also. This is a B and C because there are 2 units in between. So 1, 2, 3, 4, 5, and 6 proton because this is a germinal proton, and again one more spin system, 2, 3, 4, 5, and 6. So you see now here you have spin locking of this, and this. As a result, you would be able to record a separate NMR spectrum of D, this is D, separate NMR spectrum of B, and separate NMR spectrum of C. Now, mention that it is an extremely powerful technique. You have not hydrolyzed it, you have not only chopped it. What you have done is that still you are able to record a separate one-dimensional NMR spectrum by using a total correlation spectroscopy of this carbopeptide. A very, very powerful technique. Any question?
इसके और जो 2D sequence है टॉक्सी का मान ली और 2D टॉक्सी का इसमें तो T1 का difference
एक्चुअली जो टॉक्सी जो वन डायमेंशनल रिकॉर्ड करते हैं वो एक डिफरेंट प्रोसेस से करते हैं, उसमें T1 नहीं होता. वहाँ पे बुनियादी तौर पे in total correlation spectroscopy of one dimensional type is actually selected on the basis of one particular proton, and then you take a constant pulses to find out the remaining part of the molecule. It's just like a multiple of coupling. जैसे डबल रेजोनेंस नहीं होता है, ऐसा मल्टीपल रेजोनेंस होता है. But in case of TOXI, it is primarily a very simple technique that you take a slice of it. What you do, you get a TOXI of a spectrum and you say to your NMR spectroscopist that give me a slice of this. This is your slice. Okay? So you say that I want to have a spectrum of this particular region, 4.6 say, ye mujhe chahiye, this particular line, I want to see this particular line. And they would record this particular line for you and they would turn it for you like a peak because they always exist as a peak. So when you get the peak, you would get the peak like this. They are the same contours. They are the same contours as you have in 2D NMR spectrum, but you can ask them to record one-dimensional slices. You can ask them to record a one-dimensional slices of the 2D spectrum. So it's really, and kindly remember that you can get one-dimensional slice of every 2D spectrum. It's not a problem. COSY 45, everything, whatever you have, you can ask them to record a particular region for you. A particular region, and they will just show you that particular region. Usme jo peaks hongi, the peak which you see, they will show it in a very different way. They will show it these peaks as regular frequency peaks, because always remember that they are regular stacked peaks. They are regular stacked peaks. You're just seeing them from top to bottom. So you can record the one-dimensional spectrum of this. And for example, in this particular case, a 2D was recorded, and in this 2D, every spin system was separately recorded. And I can give you some more examples of it. For example, this. Now, these are 2 sugar molecules. These are 2 sugar units linked with each other through a beta glycoside linkage. This is anomeric proton. The anomeric protons. Now, these 2 sugar units are different from each other because one has an O methyl and the other doesn't really. So there are 2 different types of spin system. This is one spin system, and this is the other spin system. Now, I want you to understand this spin system. A spin system means this proton is coupled with this proton is coupled with this proton is coupled with C4 prime, C4 prime is coupled with C6 5 prime, C5 prime is coupled with C6 prime. So this is a spin system. There is nothing in between which is breaking the coupling. They all are coupled to each other. But this is a separate spin system because this is not coupled to this one. There is no direct coupling and C4 prime. There is no direct coupling between them. As a result, this is a different spin system and it is a different spin system. Now, if I ask you that I will have a separate spectrum of this and this, then it's so easy, because what you do that you try to find out the most downfield proton, and this is the most downfield proton, this one. This is the most downfield proton in this particular spin system, H1 prime. This. And this H1 prime is coupled to every proton in the spin system, different from the COSY. Because in COSY you can only measure the geminal coupling and Wesnel coupling. In this particular technique, you get a coupling between all the protons of a same spin system. So this is one spectrum, and the other is this one, C4. And this C4 or this C1, actually this is an anomeric proton also, so C1 is where C1 is. C1 is somewhere here, merged to this. ये deuterated water के साथ ये है, this is C1. And this C1, this particular H1 is coupled to so many protons. 1, 2, 3, 4, 5 and 6. All of these protons are coupled to each other, and then you get a separate spectrum of this particular peak, of this particular spin system. Are you convinced that you are getting a separate spectrum or not? This is one spectrum, this one, straight line, right? This is one spectrum of this spin system, and this is the second spectrum of, and if you tell them that you want a one-dimensional slice, if you want a one-dimensional spectrum, they would just cross it up, record it and tilt it for you. They just record it, get the slice and tilt it for you as you want to see them as a one-dimensional NMR spectrum. So it's a beautiful technique. See here what are the technique, how in a very complex saponin chemistry or a very complex carbohydrate chemistry, what people used to do. People were used to hydrolyze different sugars one after the other. And then they used to record and identify either by co-TLC or by recording proton NMR spectrum. Here you don't do anything. You're not really breaking this ether linkage. You're not breaking it. What you are doing, that you are using proton spin system, locking them together by using a 16 Malif 180 spin sequences, putting them together. They are locked with each other and they are locked with each other also. So they are locked as a one spin system and they are locked as a separate spin system. And in this particular case, if you are recording a COSY will show you only the coupling between this proton and this proton. That's all. You know, the COSY will never show you coupling between this and this, because this is too far away from COSY. In TOCSY spectrum, since they are spin locked, all of them are coupled to each other. All of them coupled to each other, and they are not coupled to the second spin system. They are coupled with only one within the one spin system. So this is the one NMR spectrum, and this is the second NMR spectrum. All proton of the same spin systems are locked together, and it's called total correlation spectroscopy, because that means that all of the proton of the system, total proton, are correlated with each other. Total proton are correlated with each other. In COSY, only geminal and Wesnel couplings are visible. In TOXI, all the couplings between spin systems are visible, and it is a very powerful technique because it really takes you beyond a conventional acid hydrolysis or basic hydrolysis, and you can record the NMR spectrum of so many of these compounds. Now, this is again the same thing. What you have done is the following. You ask them to give you a slice of this and a slice of this. And what you get at the end of the day is the following. This is your combined NMR spectrum. This is the of this, and this is the spectrum of this. I'm sorry, this is the spectrum of this particular. So you get a proton NMR spectrum of each system separately without hydrolyzing them. Very, very powerful technique, an extremely powerful technique, because it gives you a liberty of recording separate NMR for each spin system. A very powerful technique. And you see it here also that this is a B. Remember, this is the slice of this one. Kindly remember this. Remember this one. This 1, 2, 3, 4, 5, 6, 7 different protons. And this is the slice of the other is a slice of this one. 1, 2, 3, 4, 5, 6 or 7 protons or something like this. Here you see 1, 2, 3, 4, 5, 6, 7 proton. All 7 proton of the spin system. 1, 2, 3, 4, 5, 6, 7. 7 proton of the spin system. Remember, OH are not visible because you're recording it in a water, partially deuterated water. And remember, all OH are exchanged with deuterium. All OHs are exchanged with deuterium, and you don't see any OH. That's why I'm talking about is a spin system which is related to geminal protons of hydroxyl groups. So this is one spin system, and this is the other spin system. This is this one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7 proton of this spin system together. So it will give you an amazingly powerful technique which can record separate NMR for every separate spin system. Okay? You see, interpretation is much easier for you because when you look into one, for instance, in this case, this is the most downfilled proton in this anomeric proton. And then you can easily trace the coupling between all of them. That's why it is always handy and easy to start from the most downfilled proton, because very often in the downfield region you have less crowding. You have less of proton signals in downfield region. Now, a real life situation. This is a compound which we have isolated. This is the molecule. This is a flavonoid. There are 2 sugars here, and there are clearly several spin systems. This is one spin system. This is second inverse spin system. This is third spin. This is isolated proton. I don't know whether you'll say spin system, but this is, of course, isolated proton and nothing else. So there are actually 3 different spin systems. These are aromatic protons, and this particular region is 2 sugars, right? And you see a great deal of overlap. If you record a proton NMR spectrum, a simple proton NMR spectrum, you would see a great overlap between all sugar protons. They all are almost at a similar position. Even if you record a cozy correlative spectroscopy, you would see the same overlap. Because all peak, you would not be able to correlate between this and this and this and this, because they all are together at the same place. What TOXI does, it will give you a separate NMR of this and a separate NMR of this. So this is the beauty of it. This is the separate NMR of this particular terminal sugar. Terminal sugar. This is H, the triple prime of this particular proton, and you see all these protons of this spin system are visible within the one-dimensional spectrum. What is actually happen that you record a 2D and then you tell them, okay, slice the whole thing for me. You know, starting from here to here, I just want to get a one-dimensional NMR spectrum because it's much easier and remember in 2D, you miss something extremely important. You miss this fine structure. In 2D, you miss this resolution, doublet and triplet and quadruplet. You miss all of it because in 2D you see everything as a contour. So the fine structure are lost in 2D. 2D is so good, it gives you lots of powerful interpretation skills. You can correlate different things together because, for instance, I told you that in proton NMR spectrum, you know precisely that there's so much of information about the coupling, right? If a coupling constant is similar, it means that they are coupling partners. In COSY, you just cross the lines, you link them together. You link them together and it's so handy and easy. But if you really want to publish this data into a good journal, very good journal, where people would like to see a coupling between this proton and this proton in a real world, you always have to go to one-dimensional NMR spectroscopy or a TOXI where you can record a one-dimensional structure. So these are the peaks, same peak which you see in 2D, but when you record a one-dimensional version, remember it's not 1D spectrum. This is just a slice of a 2D spectrum. Please kindly remember that this is not a one-dimensional spectrum. It is just a slice of 2D because there is a fundamental difference between one-dimensional and two-dimensional spectrum. In one-dimensional spectrum, the whole toxic sequence is substantially different. So you see that the final structure will tell you that these doublets, these small couplings will tell you that they are actually coupled to long range from one to other. So that's how you learn TOXI, but let me take you through again this particular pulse sequence which I showed you earlier, and I want you to think over it. In COSY correlated spectroscopy, you have only two pulses, 90X pulse and 90Y pulse, only two, and you give in between a T1 time. And then you have problem with the antiphase, you have in-phase or antiphase peaks. When T1 is small, you have largely in-phase peaks. When T1 is large, you would have closer to antiphase peak and you get unmodulated from in-phase and modulated from antiphase. In this case, this 90Y pulse is replaced by a train of pulses. Train of pulses called continuous pulses. Y means number, and it's called MLEV, Malev. I don't know why it's called Malev 16. 16 means there are 16 pulses, and these 16 pulses are all uniformly placed. They have exactly identical delay in between, exactly identical for all transients. For all experiment, it is exactly identical. It is exactly identical, but they would find these splitted signal because of a chemical shift at a different place when there is a different T1. Agree? When there is a different T1, they would find them at a different place. Okay? So when you would find them at a different place, then the spin lock would lock them together. You would still have a chemical shift differences, but what would not be affected is the splitting because of coupling. Coupling splitting cannot be in a homonuclear sequence, cannot be mixed together. Cannot be mixed together. The conversion, the divergence because of coupling would continue to operate throughout the process. But only thing which would happen that all the proton of a spin system will be locked by using a particular pulse sequence. It is very close to. You have a different energy levels, and by giving energies to them together, you put them at one place. So the chemical shift difference between them minimize, coupling remain operative. As a result, all the protons of a spin system are coupled to each other. All the protons of a spin system are coupled to each other by using a particular technique in which you use a so-called locked vector diagram, a spin lock system. Okay? And that's how you record Toxi spectrum. This is a 2D Toxi spectrum of this very simple molecule. And remember the difference between this and the earlier one which I showed you. Here you see only the germinal couplings, germinal couplings and vicinal couplings, nothing else. But when you record a Toxi spectrum, actually there was a Toxi also. That's how you get the peaks between the coupling between all the protons of the same spin system. The C6 is coupled to all the protons of a spin system. All of them are coupled to each other. Okay, any question regarding this? It locks all spin systems separately from each other because they have different energy levels. For instance, when you saw the sugar, this particular sugar, the H1 of anomeric protons had a different chemical shift. And these chemical shifts is actually used to lock them together. So you lock one particular spin system and then you lock the other particular spin system in a different Toxi experiment. But you lock all the spins of the same spin system together at the same time by using a train of pulses, 16 180Y pulses, which are so-called spin echo pulses. Okay?
So if a molecule contains 2 or 3 sugar moieties, so how one can tell the NMR spectroscope, is it what he or she needs to look for? What is the procedure for finding the right sugar moiety?
Yeah, number one, you go for one-dimensional NMR spectrum, and you determine that it is fairly complex, it cannot be solved by using 1D. Then you go for a Cozy spectrum, and you determine that there are lots of overlap, and even in correlated spectroscopy, you would not be able to correlate them. And then you go for a Toxi, and you tell them in a Toxi to NMR spectroscopist to be very precise that there are certain chemical shifts which need to be separated from each other. For instance, there are 3 anomeric protons, and the 3 anomeric protons are then become a standard sets of so-called Malève pulses through which these spin systems are locked separately from each other. And as a result, you get 3 different NMR of 3 different spin systems, Toxi. Now in modern NMR and now in modern spectrometers, you don't need to tell them, because they identify 3 different proton in the downfield region, and then they conduct a 3 or 4 or 5 or 6, as many spin system as you have a separate spin lock experiments separately from each other, and it's a very, very powerful technique. At the end of the day, you get a 2D TOCSY, and in 2D TOCSY you get correlation of every spin, every proton of a spin system separately, and then you record a 1D of TOCSY in order to see which one is a separate spin system for a proton NMR spectrum.
Sir, if there are 3 anomalies protons, so 3 separate experiments need to be recorded?
Yes, the 3 different TOCSY experiment would be recorded, and there would be a 3 different Mali sequence which would be locked in on the basis of, बिल्कुल ऐसा है जैसे if you have a rope, if you have a rope and you want to connect, if you want to hold one part, you take then one part and then you grab the other part by just circulating it. You use a chemical shift of one particular proton to lock all the protons of the same spin system. But it is done automatically. It is not manual process. 2D TOCSY is a process in which the spin locking is carried out almost separately, and at the end of the day you get one single 2D experiment in which you see spins of every particular lock system. Every particular spin system is visible in 2D NMR, 2D TOCSY. Okay? Anything else? You were happy with the inadequate spectrum, the way interpretation is done? Right? It's very easy. You just have to have a horizontal line, a straight line, and then you need to have a vertical line. This peak and this peak is exactly the same. You just need to correlate it with the other spectrum. So it's easy. Similarly, in a very complex system like this, you can have a variety of different types of correlation. But the philosophy of interpretation is primarily very, very simple, that you have a straight line and then you make a vertical line, you link them together, and that's how you get a complete chain of carbon-13 framework. Complete chain of carbon-13 framework. And remember, the pulse sequence is very, very simple. As I told you, that you need to remove a strong only carbon-13 signal from the satellite peak, a rare diluted spin in which you have a C13 next to a C13. That is the only thing which you need to do. It's called filtration. This is a process through which you separate one type of peak from the other type of peak, and this is called quantum filtration. The philosophy is not that difficult. Interpretation is so easy, and therefore inadequate is a very, very powerful technique. Now I want to move forward to a very interesting technique which heteronuclear inverse technique. Now this technique, although I would really start it tomorrow, but I want to give you glimpses of what I mean by this. You see, in a normal polarization spectroscopy, you have a polarization transfer from more sensitive nuclei to less sensitive nuclei. As a result, you see an increase in the signal of carbon-13 because you were able to transfer polarization from more sensitive to less sensitive, and you have a greater difference in population, and when you have a greater difference in population, you have a greater peak intensity, right? Now, what is the advantage of it? Is a sensitivity gain. Is a gain of sensitivity. You increase the sensitivity by using a novel approach which is independent of hardware, which is independent of data processing, what you have done, you have used a selective population inversion pulse sequence through which you were able to transfer the polarization of more sensitive nuclei such as proton into less sensitive nuclei such as carbon, right? Now, I want to ask you a fundamental question. Which one is more sensitive? Proton, right? Which one is more selective? Carbon. Because carbon has a broader chemical shift range. The overlapping of signals in carbon-13 NMR spectroscopy is relatively rare as compared to overlapping in proton NMR spectroscopy. So, in a normal polarization transfer experiment, you take the benefit of a sensitivity of proton and transfer to carbon, and you see a greater sensitivity. Now somebody thought that why can't we do the reverse? If it is possible, you can do the same thing. What you have to do, what you have done in case of proton, in case of a proton, where you had an anti-phase doublet and you gave a coupling like this, and it moved from Z and negative Z. Remember this inept pulse sequence? Never forget that. And you do exactly you do it with the carbon and you transfer that to proton. What will happen? The proton will become more sensitive? क्या हो जाएगा? The intensity will increase or decrease. How much? Forget natural abundance. 1/4. It means that the intensity, sensitivity of proton will be at least 1/4 of a normal proton when you have an inverse polarization transfer. When you have an inverse polarization transfer. But what you have done in the process, you actually labeled your proton with the carbon. Now you can see carbon through proton. You can see carbon through proton. Remember, always kindly remember that when you mix, these are the scalarly coupled proton and carbon. They are scalarly coupled proton and carbon. In case of a normal polarization transfer, you transfer the polarization from the proton to carbon and you detect carbon, right? Enhanced signals of the carbon. If you do exactly the opposite and you detect the proton, what will happen? The intensity will decrease, but the carbon labeling will be visible. The carbon would be visible with the proton because carbon has mixed with the proton. Carbon has mixed with the proton. You have not detected proton in a normal polarization transfer experiment. Remember, proton was used just to generate the Z and negative Z population inversion. That's it. You have done nothing after that. Proton was just forgotten at that stage. Only carbon-13 was detected. If you do exactly the reverse and you transfer the polarization of carbon to the proton and you detect the proton, the intensity would decrease. Intensity would decrease, but the carbon is now labeled, the proton is now labeled with the carbon. It's called inverse NMR spectroscopy. Very, very powerful technique. Now, I will ask you that it is called proton detected carbon-13 NMR spectroscopy. Proton detected carbon-13 NMR spectroscopy. It primarily means that you are actually detecting the proton. You're detecting the proton, but you are actually detecting the proton which are labeled with carbon. Labeled with carbon. Any carbon which has no proton would not be detected, number one. Only those protons which are connected to a carbon through a scalarly coupled spin system will be labeled from carbon to the proton. Now proton is showing you the carbon. Proton is showing you the carbon. Question: proton, despite the fact that it has lost the sensitivity to 1/4, despite the fact that it has lost sensitivity of the 1/4, is still very powerful as compared to carbon, because carbon is 6,000-fold less sensitive as compared to. Now you are detecting carbon in proton. This is the S detected carbon, and it is only 1/4 of a proton. Is this carbon-13 NMR spectroscopy, so-called H detected carbon-13 NMR spectroscopy, is more powerful than a normal carbon-13, or yes? No or yes?
Yes.
Absolutely. Despite the fact that proton is 1/4, despite the fact that proton is now 1/4 of the intensity, but you are now seeing carbon through proton, and it is a proton NMR spectroscopy by all definition. Despite it is 1/4, it is at least 1,000-fold more sensitive than a normal carbon-13 NMR spectroscopy. So it is, yes?
Sir, why can't we transfer polarization first from proton to carbon and then carbon to proton?
That's what we do actually, always. I remember I told you earlier also that we become very smart after understanding polarization transfer. Polarization transfer is a cross-cutting phenomena now. Polarization transfer, you have seen in COSY, this was a polarization transfer from proton to proton. You've seen a normal proton polarization transfer to carbon, and you see a sensitivity gain. Now, if you have inverse, a traditional inverse NMR spectroscopy, traditional, when it was discovered in early 90s, when carbon polarization was transferred to the proton, you were able to have an excellent, nice proton detected carbon-13 NMR spectroscopy, because proton in, even it is 1/4, it is much more sensitive than carbon, and you were able to see carbon peaks in proton detected NMR spectroscopy. Now, what is now happening is exactly what Dr. Athiya is mentioning, that they do a reverse. The first transfer from proton to carbon, and then from carbon to, so that gain is wonderful. You don't really lose anything. It becomes extremely powerful technique. Proton detected reverse correlation inverse NMR spectroscopy is one of the most important development in NMR spectroscopy. If you give me, if you allow me to have a 4 major development in NMR spectroscopy, I would say number 1, pulse Fourier transformation NMR spectroscopy. Number 2, polarization transfer NMR spectroscopy. Number 3, inverse NMR spectroscopy. In my opinion, these number 3 and number 4, so-called hyphenated NMR spectroscopy, or use of so-called coupled NMR spectroscopy. These are the 4 most important development in terms of a real human ingenuity. As far as the development of a larger magnet is concerned, was so obvious, it was very, very obvious that you would have a greater magnet, you would have more of polarization. It was not a real development, and it was borrowed from already developed superconducting magnets. Superconducting magnets were developed long time ago, and they were used in NMR spectroscopy, borrowing a technology. Probe technology was a technology of laser guns and other things, Lots of parallel technological development took place. Computer were developed as computer was developed over the years, But if you really look into a novel things which actually happened in NMR spectroscopy is, number 1, pulse Fourier transformation spectroscopy, which has changed the complexion of a technique from absorption to different technique. real polarization transfer NMR spectroscopy, which gained in a novel way the sensitivity of a weak signal and make it possible for people to detect carbon-13 or N15 or other poorly sensitive nuclei, and then the inverse NMR spectroscopy, in which you are now able to see in proton detected manner carbon-13, proton detected manner N15, proton detected manner any insensitive nuclei which is connected to a proton, or proton or a phosphorus, carbon, whatever, you just name it. More sensitive nuclei is now used as a mirror to see the less sensitive nuclei in a very inverse manner. So this is an extremely important development, and we would go a great deal of time spent on this in order to have a basic understanding how inverse experiment work. But remember, when we have a normal traditional polarization transfer, we use the sensitivity of proton to increase the sensitivity of carbon. Exactly, the proton is labeled in carbon. Always remember, because proton has given its polarization to carbon. Always remember that in EPT, which is the component of most of the inept or depth experiment, proton is labeling the carbon. Proton is not discrete. Proton is making them go to the negative phase or a positive phase. This is because of the proton. This is because of the proton that two of the peaks appear in positive phase and two of the peaks appear as a negative phase. So the carbon is actually labeled with proton, and you are detecting proton through carbon. You say this is CH2, right? This is CH3, this is CH. Here exactly the opposite taking place, in which proton, the carbon-13 is transferring the polarization into proton. Sensitivity increase, but proton is now labeled with carbon-13. And when proton is labeled with carbon-13, you see the carbon-13 through proton. It's a H-detected NMR spectroscopy, and it is a one novel way of increasing the sensitivity by just looking everything in a mirror of proton, more sensitive nuclei. It is an extremely powerful technique, and there are lots of experiments, HMBC, HMQC, HSQC, there are a number of other variants of inverse NMR spectroscopy. There are hardware requirements also, because you need to have an inverse probe which is capable of modulated carbon-13, which detect only proton, not the carbon-13. So there are lots of hardware requirement also, but inverse has become a mainstream, very important technique in NMR spectroscopy. We'll discuss that in greater detail. I thought I'll introduce you to this particular technique, and there are actually two large techniques, HMQC and HMBC, and these two techniques are very extensively used now in structural elucidation of molecule. Now, I want to ask you, what are the challenges remain? You see, if you look into NMR spectroscopy in terms of development, you had a challenge of sensitivity, right? You had a challenge of sensitivity which you solved by using polarization transfer. Okay? You had the challenge of interpretation which you tried to solve by using apt experiments and other thing also. Even then you had a problem of great overlapping, so you went into a second dimension by using two-dimensional NMR spectroscopy. In two-dimensional NMR spectroscopy, you said that homonuclear correlation with COSY can only have geminal and Wassermann couplings, and even that can have a great overlap. And therefore you would not be able to recognize which peak belonged to which particular spin system. You went into a very novel sequence called TOCSY, total correlation spectroscopy, in which you were able to identify every spin system separately from the other by using the same predictive value of NMR. Remember, NMR is a strong technique because it has a predictive value. It is a technique in which actually happen. Manifestation, आपके action का, what is the result of your action? What is the result of a 90Y pulse? What is the result of a 90X pulse? And what is the results of 16 180 pulses? You know all of it. It has a great predictive value. So you got this tremendous capacity of recording a proton NMR spectrum of every spin system separately by using a 2D Toxie and slicing out various regions of 2D spectrum. Then you got this tremendous capacity of correlating a very dilute and rare spin. Proton, carbon, carbon 13 next to carbon 13 also. There are great variants of it. Now you have a problem that despite the fact that inadequate is so powerful, it is very insensitive. So you remain with certain problems, and these problems are then solved by using HMQC and HMBC. Which proton is connected to which carbon? This is a problem remain. Remember, you don't have any technique so far which we have discussed in which you know which proton is connected to which carbon. And you also don't know which proton is connected to which carbon in a long range. So you cannot then piece them together. You cannot gel them together. You can have different spin systems, but you cannot put them together without information about the long range coupling. So there are lots of challenges. And eventually at the end of the day, when you would have a structure, you would not know what is the conformation of it. So you would need an NOE, nuclear over effect, and that's what NMR spectroscopy is. That's it. Finish. In terms of structural elucidation, these are the techniques. Now there are other variants of NMR spectroscopy. NMR is used in medical diagnosis. NMR used for mixture analysis is a different techniques altogether, DOSI and all that. But the purpose of other technique is not to determine the structure of a single molecule. It is rather for tissues, it is for the mixtures of different types and different other. But for structural elucidation, this is primarily the techniques. Normal proton NMR, carbon 13, decoupled, coupled, at polarization transfer of different types, correlated spectroscopy, heteronuclear multiple quantum coherence, HMQC, HMBC, last at the end, nuclear overlap effect, and N of it. This is the N of NMR spectroscopy for structural elucidation. And next time, inshallah, tomorrow, we would have HMQC, and day after tomorrow, we'll have a long class starting from exactly 2 o'clock to 8 o'clock in the night. We'll discuss lots of other NMR techniques. You see, remember, NMR is much more important than match. So we'll start right a minute before 2 o'clock, and we'll finish somewhere between 7 to 8. Okay? There are some brave people who said yes, no problem. Okay, we'll discuss tomorrow what we'll do day after tomorrow. Okay? Thank you. Thank you very much.
get a message